Say that one builds a do-it-yourself NAS by getting a couple of hard drives and stick them into a SATA cabinet, attach a Raspberry Pi 4 via USB and connect the system to mains and to the network. What kind of reliability could one expect from such a solution? That is what we are about to explore in this video. The following items are used in this setup. The Sabrent hard disk cabinet. It contains a fan, 4 slots, and electronics to convert USB to SATA. It does not contain any RAID functionality. The power supply that came with the case, 12 volts and 6.5 amps. A standard Raspberry Pi 4 with 4 GB of RAM, and it has a proper heatsink. The standard Raspberry Pi power supply, 5 volts and 3 amps. The SD card used with the Raspberry Pi is a SanDisk Ultra, 64 GB. All the following drives are 3.5-inch and carry 2 TB each. A Toshiba PCP300, a 7200 RPM hard drive, and it is marketed towards high performance rather than a server or NAS application. A Western Digital drive, a DC HA210, marketed as a server or NAS drive. One Seagate Barracuda ST2000D, also a 7200 RPM drive, and marketed as super reliable. Another Western Digital from a different product line, WD20EZ. If the other drives were fresh off the production line, this is the bad boy. It is bought refurbished. Why would I ever include a refurbished drive in a NAS? We will find out a little bit later. In order to compute the reliability of this NAS solution, we now only need the reliability data for these components and the potential failure modes, and we're all set. However, these components are of commercial or consumer level quality, in contrast to, say, automotive, defense, aerospace or any other industrial grade. This means that there is very little data on the reliability of these components. In fact, for some components there isn't any at all. We will have to use some detective work and experience and some guidelines from the field of reliability engineering to assess these components. Let's start with the Raspberry Pi. The Raspberry Pi Foundation has not published any proper reliability figures, so we need to take a look at its key components. Before we start to fill out the figures here, we need to ask ourselves, how do we model electrical component reliability? We need to briefly discuss the bathtub curve. On the x-axis we have operating time, where t equals 0 means when it's first put into operation. We are only considering continuous operation here. On the y-axis we have the probability of the component failing per some unit time. Typically it's the probability of failure in 1 operating hour. On the left-hand side we have the region of infant mortality. The probability of failure is elevated due to imperfections in production. Low quality units pass the factory tests but fail early in life. The process of reducing this rate is sometimes referred to as burn-in and may include high temperature or high voltage testing. At the other end of the scale we have the wear-out or old age region, where the failure probability is elevated due to the aging process, where components reach end of life. In between we have the normal life or useful life, that is after the initial problems and before the aging really sets in. A very common model assumes the failure rate is fairly constant in this period. Not that the actual rate is very flat, but it's an approximation that allows for an easy analysis. Since the rate is assumed to be flat, are errors just as likely anywhere in this region? This is sometimes referred to as random hardware failures, that is, unpredictable errors that has nothing to do with aging or production problems. Given that we have a constant failure rate, we can compute the probability that the system is still working after some time, or conversely that the system has failed after some time. The curve looks like this. The green is the probability of survival, and the red is the probability of failure. The curve is plotted with a constant failure rate of 1 failure per 10,000 hours. Given the random nature of the problem, there is a probability that we will fail before the 10,000 hours mark, but also a probability that we will survive past the same mark. It turns out that the 10,000 hour mark is the average time for the system to fail, also known as the mean time to fail, or MTTF. Under the constant failure rate assumption, the MTTF is the inverse of the failure rate. Let's go back to the Raspberry Pi 4. Should we use the reliability function, the MTTF, or the failure rate to estimate the total reliability for the Pi? The easiest to use the failure rate, lambda. To see why, let's make a little diagram with some components connected from left to right. All these components are necessary, so if one fails, the system will fail. So therefore, all component failures lead to system failures. This means that we can add the individual error rates to get the system failure rate. However, if we would have some redundant components, say like if we would like to use both Ethernet and Wi-Fi, these would show up in parallel, like this. If only one of these two would fail, but not both, the system would still be operational. One would then need to compute the equivalent failure rate for the combination of the Ethernet and the Wi-Fi. This style of diagram, where one uses boxes in sequence and in parallel to illustrate the relationship between component errors and system failures, is called a reliability block diagram. We will get back to this when we are discussing hard drive redundancy. For the Raspberry Pi, I only use Ethernet, so we can just sum up the individual error rates. Now then, let's find the failure rates for the key components. We start with the SoC, the Broadcom BCM2711. Unfortunately, Broadcom has not released these figures. In fact, it doesn't seem like Broadcom has publicly released any design documentation for this SoC. Other companies like Xilinx provides rather comprehensive reliability reports for all their components. Xilinx releases this report semi-annually and has a lot of information about the reliability of their components. On this page, we find a definition of a very common failure metric for random hardware failure rates. They define FIT, which is read out as failure in time. The failure rate is defined in FIT units. 1 FIT equals 1 failure per billion device hours. For example, 5 failures expected out of 1 million components operating for 1,000 hours have a failure rate of 5 FIT. They also list their components and their measured reliability. Obviously, they do not have 1 million units to run for a long time to test the real error rate. Instead, they do temperature accelerated testing. The theory here is that by operating at high temperatures, one may simulate the behavior of a device operating for a long time at normal temperatures. At the heart of this theory is the Arrhenius equation, which says that the speed of a chemical reaction increases exponentially with the temperature. Unfortunately, we cannot go into that theory here. Let's take a quick look at one of the famous devices from Xilinx, the Zinc 7000 series. They have tested 404 circuits at some higher temperature than 125 C, probably 130 or so, and accumulated in total 808,000 hours. That means that they have probably run the lot of 404 samples for 2,000 hours straight. When this result is recomputed to 125 C, that corresponds to over 1 million device hours. And at normal operating temperature of 55 C, it corresponds to more than 80 million device hours. So by using a couple of hundred devices and elevate the temperature by 70 degrees or so, they have accelerated the testing by a factor of 400,000. In this way, Xilinx may conclude that the devices will have a failure rate of 11 FIT, or have 11 failures per billion operating hours at 55 C. This could be recomputed to say that the average time between two failures is about 90 million device hours. However, this is a characterization of the behavior of a big number of circuits for a relatively short time, rather than the expected life of a single component. After 90 million hours of operation, or 10,000 years, A device would no longer operate in the normal life domain, not by a long shot. It would have died of old age a very long time ago. This measurement is only used to establish the floor of the normal life operation, not the expected life of a single device. Since Broadcom does not publicly release any reliability reports, we cannot really know these figures. But let's make a guess anyway. An SoC comes in a package that looks something like this. At the very center we have the silicon die. It sits on top of a substrate and under a metal lid or a plastic lid, and the substrate is connected to the circuit board by soldering balls. We saw that the failure rate of the Xilinx device was quite low, only 11 fit, and we don't know this figure for the Broadcom device. However, it might be possible to ignore this, since 99% or so of the failures occur at the interface between the SoC and the circuit board. Breaking soldering joints is a real killer, and that may contribute to thousands of fit. That the silicon die has 10 or so can mostly be ignored. The properties of the soldering joints are determined by the manufacturing process. So we are going to take the same route as some of the reliability standards out there, like ISO 26262 or SN 29500, and assume that the failure rate is proportional to the number of balls or number of interconnects. But how good is the Raspberry Pi production process? We don't know, but we have a figure from a Raspberry Pi engineer. The estimated life of the SoC is 40 years. Note how he says that they use the standard industry way of sticking chips into an oven. To me it sounds like they have estimated the fit rate during the normal life of the SoC and then recomputed that to an MTTF figure. But for our purposes we are interested in the fit rate, so let's convert the MTTF figure back to the fit rate. 4 years would correspond to 2854 fit. That is quite high for such a relatively small SoC, so it's probably not just the silicon die. After all, it is 300 times that of the Xilinx device that we looked at earlier. I suspect that it includes the entire package and the PCB soldering. I estimate that the number of balls is approximately 400, but this could be off by some factor. Anyway, this would mean that the Raspberry Pi production process would yield about 7 fit per ball. That is more than twice than I expected. Comparable figures in the automotive industry would be about 1 to 3 fits per ball, but then again the quality requirements are much stricter than in consumer electronics. Let's use this information and assume that all the solder joints on the board have the same reliability. The memory has 200 balls, which yields 1420 fit, and in the same way we may compute the contribution for the other major chips and throw in some figures for the passive components and transistors, and finally we add some figures for connectors, the PCB itself and some other stuff, so that we in total get around 8800 fit for the entire Raspberry Pi 4. Now we may estimate the MTTF in the normal life region to be 12.4 years. Again, this is only another way of saying what the floor level is during the useful life. It says next to nothing about the aging process or how old a Raspberry Pi may become for a certain operating condition. When it is set in a harsh environment condition with vibrations and large temperature variations, it is not likely to reach 12 years. But if it's used in an office environment with low humidity, no shaking, and constantly on at 25 degrees, it may very well last 12 years. It depends heavily on the environment and how lucky you are. For the NAS, the environment will be the latter, quite well controlled. That big heatsink will keep the CPU temperature to no more than 40 degrees. There will be no vibrations, it's constantly on and never moved around. Therefore, I will go out on a limb and assume that the failures will be dominated by random hardware failures rather than aging processes for up to 10 to 12 years. I may be wrong, or I may be unlucky. I guess only the future can tell. Next up is another reliability suspect, the SD card. Now this is an interesting field. let's have a look at the OEM manual for one of the major manufacturers, SanDisk. In the chapter for reliability, they state that the MTBF is over 1 million hours. I have a couple of issues with this. The first and the most obvious is that they use the term MTBF and not MTTF. The MTTF applies to a system that can break. It is defined as the mean time it takes from operation start to failure. However, if the system can be repaired, then we can bring back the system to operation when the system is mended. Then we talk about the two other metrics, MTBF, which is the mean time between failures, and MTTR, which is the mean time to repair. MTBF only applies to repairable systems. An SD card is not repairable, at least not with my skill and equipment. This mix-up is very common. The other problem is that they state the MTTF to be over 1 million hours. This is misleading to say the least. 1 million hours correspond to over 100 years of continuous operation. I do not for a moment believe that such a device would survive for that long even under favorable conditions. I think that this, again, is a converted failure rate deduced from the accelerated test that has no implication on the real lifetime of the device. It is perhaps used for statistics for a large fleet of units for short periods of time, but it's not the expected life of a single device. SanDisk is not alone. Everybody in the SD card industry seems to quote ridiculous MTBF figures, with ATP Industrial taking the prize with 5 million hours. We cannot use these figures for our purposes, so let's get a little bit creative here. When a company puts a product on the market, it probably has some idea what the expected life is, at least for economic reasons. If we take a look at the bathtub curve once again, the area under the graph shows the failed units up until the end of life. These are all potential customer returns, and customer returns are very expensive. They eat away on the margins of the company. Therefore, this area should be no more than 1 or possibly a few % of the produced volume. Therefore, the expected life should be on par with or higher than the warranty. This is a somewhat shaky reasoning, as there is a lot of stuff going on in sales and marketing, but I still think somehow that the warranty figures are a better indicator of life than the quoted a few million hours. So let's pick 5 years of warranty, or MTTF, or 43,800 hours. That corresponds to close to 23,000 fit. Next up is the power supply. Here I am out of my depth, because this is tricky. I don't want to pick this supply apart just to analyze it. I know there are a few components that can fail inside, like a transformer, a switching transistor, or some capacitors. I'm going to model the reliability as one giant capacitor, partly because it has the potential of ruining the entire power supply design, and partly to show the importance of good design. Let's visit Vishay's capacitor reliability calculator. Specifically, I am looking at tantalum capacitors, a type of electrolytic capacitor often used in power supplies. Let's first select the capacitance. 1000 fit is in the middle of the expected range. The application voltage is 5 volts. The temperature is room temperature using a relatively good design, so 25 C. The rated voltage should be twice of the application, so let's have 10 volts, and we don't know the circuit resistance, and the reliability level is commercial grade, and the environment is assumed to be relatively okay, it's ground benign. The series isn't all that important, but when we select one of these we will get 8.47 fit, which is really good. But if we now change the operating conditions and try to select some other values, that we decrease the margins from 10 volts to 6.3 volts and have a very bad power supply or thermal design, and we are shaking a little bit more, then suddenly the fit goes up to 22,000 fits, which is really bad. And if we then decrease the voltage margins even more by saying we are operating at 6 volts, then the values suddenly jump up to 483,000 fit, which is extremely bad. This means that depending on the environment and how well the power supply is designed, we could have anything from 10 to 500,000 of fits. So whether you buy a good quality power supply or some cheap crap, it can make the difference between it dying long before or long after the Pi. Since I have the power supply from Raspberry Pi, it should, for at least economical reasons, be about the same as for the Pi. Therefore, lacking all other information, I will use a round figure of 10,000 fit. I'll just copy that estimate to the Sabrent power supply, although I suspect that it might be a little bit better due to the higher budget. Let's move on to the Sabrent hard drive case. I will split this into two parts, the fan and the electronics. I don't have any data for them either, but I will compare the electronics to the Raspberry Pi 4. It's probably less complex than the Raspberry Pi 4. On the other hand, it has much higher data rates. It has 10 gigabits USB 3 and 4 6 gigabit SATA connectors, so the design is partly high performance and therefore probably has small design margins. On the third hand, it has a larger budget than the Raspberry Pi, so it probably can afford some high quality components and a high quality manufacturing process. All in all, I put it in the same range as the Raspberry Pi, but a little bit better, about 2/3 of the failure rate. Let's have a look at the fan. Since the general build quality of the Sabrent seems quite high and the unit is rather expensive, I would expect the fan to be in the better half of the market. I'll compare it with another good brand that I've used before, Noctua. Before we put in the fit rate for the fan, I want to make a comment on how applicable the constant error rate model is for fans. The death zone of the constant error rate reliability function is very wide. If the failure rate is 1 per 10,000 hours, the first units start to fail at 300 hours, while some last up to 30,000 hours. That is 2 orders of magnitude. The reason for this is that the random hardware errors can kill the unit at any point in time, sooner or later, and that the survival function is a statistical property, not an aging process. Think of a batch of fans in which some units start to fail after 3 years. One would not expect the best units of that batch to live for 300 years. Perhaps they will last 10 years. So the death zone of a fan is much narrower than one could expect from the constant error model at the same MTTF. The reliability function falls off much steeper around its MTTF. So when we try to model the life of a fan with the constant error model, we are both over and underestimating its life. The fans will not start to fail as early as the model predicts, nor will they live past the MTTF much. Using this model adds more uncertainty than is really warranted. Having said that the random hardware failure model is really unsuitable for fans, I will use that anyway. Let's have a look at the Noctua statements. They use the correct term, MTTF, but they have a quite high number, 150,000 hours. If they really mean that per individual, they would last on average 18 years. These fans are good, but not that good. They do, however, have a warranty of 6 years, and that corresponds to 53,000 hours or 19,000 fit. Now, we have to save the rest for the next part. We will discuss the hard drives, dig out failure statistics for some 200,000 drives, get reliability figures for the 4 drives, and obtain the expected life for the NAS. I will also explain why one of the drives is refurbished and which role RAID plays for the reliability, and talk about the expected maintenance and the spare parts. Finally, I will conclude on how many nines of availability I can expect. Thanks for listening and see you next time.